Oh, didn't erase the board. This is number 5, did you say, on the homework?
Yes, that's correct.
And number 30 in the book, which would be 571, I believe. 741. Not even close. All right, so we're asked to find the Taylor series, the first 4 non-zero terms, and then write the power series using summation notation. So they're not asking for interval, radius, or interval of convergence. The earlier problems did, this one doesn't. So we can go there.
If I could interrupt, you might want to adjust your screen.
Oh yeah. How's that?
That works well.
All right. So the Taylor series, we need to find the coefficients. And we have a formula for them. They're the kth derivative. The kth one is the kth derivative evaluated at the center, 2 in this case, divided by k factorial. So for a given function, the mystery is the numerator. I mean, k factorial, that's there for all of them. And so we just need to figure out a pattern where the kth derivative is evaluated at 2. And it starts at 0, which is just the function. So let's f of 2 is 1/2. Yep. And now we'll take a derivative. Minus 1 over x squared. Evaluated at 2. So let's make like an extra column over here where we do the evaluation. -1. We're looking for a pattern, so let's not square it out. -1 over 2 squared. Second derivative. Two over x cubed, right? Bring that 2 down. It's a -2. Flips the sign, and we decrease it by 1. You good? Plug in 2. 2 over 2 cubed. Let's not simplify that yet. Again, we're looking for a pattern. We need to compute a couple more, I think. The third derivative is negative. We're going to bring the -3 down, multiplied by 2. Again, we're looking for a pattern, so don't multiply it out. And then we get x to the -4. Let me write it like that. So we get negative, I think I see a factorial showing up there. And then we have over 2 to the 4th. Okay? All right. I think one more will have it. The 4th derivative, maybe we could get it already, but we'll do one more. So comes down, bring the 4 down, the signs cancel. We get 4 times 3 times 2. We recognize that as 4 factorial. And over here we get 4 factorial divided by 2 to the 5th. All right, I think we've done enough work. We can now answer the questions. The first question says, find the first non-zero terms. So the first non-zero term is the function evaluated at the point. all the rest of them come from this formula right here, the coefficient. And the powers go up by 1 as we work our way down the list. It's a power series. So the first derivative, evaluated at 2, is negative. We'll just plug everything in here and we'll simplify it. Times x to the first. Divided by 1 factorial. Let's write it just to show we thought about it. But it doesn't really do much. All right. And then we go to the second derivative, which we have right here. 2 over 2 cubed. Divided by 2 factorial times x squared. So we'll figure out what all the pieces are in just a minute. Right now, we're not going to try to be fancy or smart. We'll just write out the details that we have. The next term, we go to the third derivative. It's up over here. 3 factorial divided by 2 to the 4th divided by 3 factorial x cubed. I made another mistake. The center is not at 0. So all of these x's need to have a -2. The center is at 2. Get out of my way, chair. Okay, Mark?
Yeah, looks good to me.
Oh. This square should not be there. First power, second power, third power.
Okay. What about the 2 in the very beginning? Wouldn't it be 1 over 2?
Yep.
Okay, sweet.
No, I looked here. Should have looked there. Good catch. Now you can clean that up, and you probably would want to clean that up before you punch it into the Pearson homework. So let's do it. Get 1/2 minus 1/4 x minus 2. Okay, we can also take a look at what's going on here. And it's especially revealing at this term. We have a 3 factorial in the numerator and the denominator. And then we see one reason why I didn't combine this 2 with those is I thought it was there for a different reason. Because it's starting to build a factorial up 1, 2, 3 factorial. So that cancels that. Doesn't do much with that, cancels that. And so we end up with 1 over 2 cubed. I guess we could cube it out for the answer to part A. And then minus 1/24. 2 to the 4th, 16. So there are the first 4 non-zero terms. Part B, they ask us to write it in sigma form. So obviously we have an x minus 2 to the power k. It starts at 0 and it goes to infinity. There is an alternating feature. When k is even, it's positive. So since I started at an even number, -1 to the k will alternate in the proper order. And the other thing going on is we have these powers of 2. And notice when k equals 0, we have 1 power. So I think I want to say k plus 1. When k equals 1, we get 2 squared. When k equals 2, we get 2 cubed. So it looks to me like that is the sigma form. Okay? Any last questions on this problem?
No, I think we're just about good.
All right, I'm going to pause the recording. So for all of these guys, we need to know the Taylor coefficient. So we have a formula for it. The kth derivative evaluated. This one is evaluated at 0, unlike the last one, over k factorial. So we need to find a pattern for the derivatives, and what a wonderful function we have. F of 0 is
1.
1. I bet you can do everything in your head. F primed of 0 is
Go with -1.
F double primed of 0 is
1.
1. F triple primed,
Probably 84.
84. Yeah, close.
Okay.
Yeah, so we get almost immediately we get this super nice repeating pattern. And so A0 is equal to 1. A1 is equal to the derivative, -1, divided by 1 factorial. I mean, technically, this is divided by 0 factorial. A2 is 1 over 2 factorial. A3, we're back to negative, right? Over 3 factorial. And so on. So P1 is the functional value 1 plus A1, -1 times x. P2 uses both of those. And then we add P2, which is 1/2. Technically factorial, but I'll write it as a 1/2. P3 is equal to all of those. I'll just call it P2. And the next term shows up, which is minus 1 over 3 factorial, x cubed. P4 is all of those. Oops, yeah, P2, they're captured there. And then we'll add in 1 over 4 factorial x to the 4th. And finally, P5 is P4 minus 1 over 5 factorial x to the 5th. If you watch the video, can you see this? My computer was angled funny. If you watch the video, I encouraged you to plug these polynomials into your calculator and see how, first of all, how these polynomials find the function, and we're attaching them at 0. So, on the y-axis. And then as you add terms, this polynomials look more and more like the function, which in this case is exponential decay. And so as we work our way down the list, just graph them, like punch in P1 and graph it along with e to the minus x and see 1 minus x, the slope is -1, the y-intercept is 1. So it's going to look something like that. It's close to the function for a little bit, but of course the function takes off. But then you take the quadratic and we can make it look like this function a little bit longer. Notice it does open up, so it knows to be concave up. And it's just interesting to plug them into your calculator and just see how adding these terms makes the polynomial look more and more like that exponential decay curve. I guess I like it because when I was a calc student, no one had ever thought yet of graphing calculators. And so, we could do the calculations, we could come up with the answer, but we never really got a very graphical example of what we were doing. We just memorized it and we did it. And now you can just pull your calculator out and you can see exactly what's going on. I mean, it's really beautiful, especially this one, the exponential. It converges for all x. So if we're just willing to add enough terms, we can make a polynomial. Eventually, the degree goes to infinity, so it's not really a polynomial, but we can make it look identical to that exponential decay curve. All right?
Right.
So the polynomials, you just find a finite number of terms. Notice it didn't ask us to write it in sigma form. We don't yet know in section 1 about radius of convergence or any of that. It's just like, here's some polynomials and here's some cool ways to approximate a function. And then in section 3, we took it further, the actual Taylor and Maclaurin series. All right, I'm going to pause the recording.